Hi, good day. We are the Group 1 and we will report about chemistry of water. But first, what is water made of? Water is a chemical compound whose molecule contain two hydrogen atoms and one oxygen atom. The chemical formula for water is H2O, and the bond between the water molecule is covalent bond because both hydrogen and oxygen are nonmetal. Next is it consists of several isotopes because as we all know, hydrogen and oxygen consist of several isotopes. Water consequently consists of more than one type of molecule, which are the protium, deuterium, and tritium. The differences in the isotopes composition of molecule is because of different saturated vapor pressure, temperature, and heat of phase conversion, heat capacity, and in the thermal dependence of thermodynamic quantities. One of the most essential compound is water because we all know that human body is made up of 60% water and about 71% of the earth's surface is covered by water. And also, we all know that water is the universal solvent because it has the ability to dissolve substances, and the basic reason for its remarkable dissolving and ionization capability of water because water has a dipole character and high dielectric constant. To further know about chemistry of water, here are my group mates to discuss further.
The world is mostly composed of water, such as the human body, which is composed of 70% of its mass with water, which is why water is very essential for life. Now, we are going to talk about water, its chemical reactions, and why it is so important. So first, water is a polar substances. So what is polar substances? Polar substances possesses regions of positive and negative charge. For example, water. The type of bond it has when coupled with its shape gives one end of the molecule a slight positive charge and the other a slight negative charge. As you can see in the figure, oxygen has a negative charge and hydrogen has a positive charge, which means the bond water has is polar, which make it polar substances. Which means polar substance is all about having a linear direction of charges that goes from positive to negative, which means all polar substances have charges that is linear that goes from positive to negative. And these polar substances are only attracted to other polar molecules such as ethanol, water, ammonia, and sulfur, and many more. Molecules with oxygen atoms, nitrogen atoms, or ionizable groups, such as negative CO2H and negative SO3H, tend to be polar.
Electrolytes are substances which, when dissolved in water, break up into cations and anions. We say they ionize. Strong electrolytes ionize completely 100%, while weak electrolytes ionize only partially, usually on the order of 1 to 10% only. That is, the principal species in solution for strong electrolytes are ions, while the principal species in solution for weak electrolytes is the unionized compound itself. Strong electrolytes fall into three categories: strong acids, strong bases, and salts. Salts are sometimes also called ionic compounds, but really strong bases are ionic compounds as well. The weak electrolytes include weak acids and weak bases. Here are some examples of strong and weak electrolytes. For strong electrolytes, strong acids: HCl, HBr, HL, HNO3, HClO4, and H2SO4. Strong bases: NaOH, KOH, LiOH, BaOH2, and CaOH2. For salts: NaCl, KBr, and MgCl2, and many more. For weak electrolytes, weak acids: HF, HC2H3O2, acetic acid, H2CO3, carbonic acid, H3PO4, phosphoric acid, and many more. For weak bases, NH3, ammonia, CH5H5AN, pyridine, and several more, all containing N.
Non-electrolyte. Non-electrolyte can be defined as substances that do not have any distinct ionic form to exist in when they are dissolved in aqueous solution. Such substances are usually poor conductors of electricity due to the fact that they do not readily dissociate into ions in their melt states or in their dissolving states. It is not uncommon for solution of non-electrolytes to be insulator of electric currents. Non-electrolytes can be alternately defined as substances that do not dissociate into ions when placed in solutions. On the other side of spectrum, electrolytes are the substances that do dissociate into ions when dissolved in solution or aqueous media. The presence of free ions in such solutions make them great conductors of electricity. Example of non-electrolyte are the chemical compounds that when placed in solution don't ionize at all. As a result, non-electrolyte contains solution that not conduct any electricity. Non-electrolyte are usually held together by covalent bonds rather than ionic ones. Glucose, a sugar with a chemical formula C6H12O6, is a typical example of non-electrolyte. Glucose, commonly known as sugar, dissolved readily in water, but because it does not dissociate inside the solution into ions, it is considered a non-electrolyte. Therefore, glucose-containing solutions are not conductor of electricity. Another important example of non-electrolyte is ethyl alcohol, also known as ethanol. This organic compound does not dissociate into any ions when dissolved in water.
The lesson 4.2, the precipitation reaction. Lesson 4.2, precipitation reaction, refers to the formation of an insoluble salt when two solutions containing soluble salts are combined. The insoluble salt that falls out of solution is known as the precipitate. And the next one is double displacement reaction. A double displacement reaction is a type of chemical reaction in which the reactant ions exchange bases to form new products. Usually, a double displacement reaction results in precipitate formation. The chemical bonds between the reactants may be either covalent or ionic.
An aqueous solution of silver nitrate reacts with an aqueous solution of sodium chloride. silver is going to pair with chloride and sodium is going to pair with nitrate. It's called double displacement reaction. Always put positive ion charge first, then the negative ion charge in equation. Rewrite the equation. For the final step, rewrite the total ionic equation. And we got reactant silver with positive charge plus chloride with negative charge to product silver chloride.
This is the producting stability. Learning objectives. Recognize the various ions that cause that salt that generally be dissolved in water. Key point. Stability is the relative ability of a solute and dissolve into a solvent. Several factors affect the stability of a given solute in a given solvent. Temperature often plays in the largest role of so pressure can have a significant effect of gases. Terms. Solute that compound that dissolve into solution can be a solid, liquid, or gas. Stability relative ability of a solute dissolved into a solvent. Solvent is a compound, usually a liquid, that dissolve into salt. Definition of stability. Stability is the ability of a solid, liquid, or gaseous chemical substance, refers as a solute, dissolved in a solvent, usually a liquid, and form a solution. That stability of substance formally defined as a solvent used as well as temperature and a pressure. Factors affecting stability temperature. That stability of a given solute in given solvent typically depends on temperature. For many solids dissolved into liquid water, stability terms to respond with increasing temperature. As the water molecules heat up, they break more quickly and are better able to interact with or break apart that solute. And this is the example. And this is the chart.
So, guidelines for predicting solubility. The following are the solubility rules for common ionic solids. If there are two rules appear to contradict each other, the preceding rule takes precedence. So, first rule, salts containing group 1 elements Li+, Na+, K+, Cs+, Rb+, are soluble. There are few exceptions to this rule. Salts containing the ammonium ion NH4+ are also soluble. Number 2. Salts containing nitrate ion NO3- are generally soluble. Rule number 3. Salts containing Cl-, Br-, or I- are generally soluble. Important exceptions to these rules are halide salt of Ag+, Pb2+, and Hg2, 2+. Thus, AgCl, PbBr2, and Hg2Cl2 are insoluble. Number 4. Most silver salts are insoluble. AgNO3 and AgC2H3O2 are common soluble salts of silver. Virtually all others are insoluble. Number 5. Most sulfate salts are soluble. Important exception to this rule includes CaSO4, BaSO4, PbSO4, and Ag2SO4 and SrSO4. Rule number 6. Most hydroxide salts are only slightly soluble. Hydroxide salts of group 1 elements are soluble. Hydroxide salts of group 2 elements CaSr and Ba are slightly soluble. Hydroxide salts of transitional metals and aluminum 3+ are insoluble. Thus FeOH3, AlOH3, COOH2 are not soluble. Rule number 7. Most sulfides of transition metals are highly insoluble, including CdS, FeS, ZnS, and Ag2S. Arsenic, antimony, bismuth, and lead sulfides are also insoluble. Carbonates are frequently insoluble. Group 2 carbonates CaCO3, SrCO3, and BaCO3 are insoluble, as are FeCO3 and PbCO3. Number 9. Chromates are frequently insoluble. Examples include PbCrO4 and BaCrO4. Number 10. Phosphates such as Ca3PO4 2 and Ag3PO4 are frequently insoluble. Lastly, fluorides such as BaF2, MgF2, and PbF2 are frequently insoluble. So, example, which of these substances is likely to form a precipitate? A. CaSO4, B. Table salt, C. AgBr. Letters A and C are both likely to form precipitate. Concerning A, CaSO4, although sulfates tends to be soluble, rule number 5 indicates that calcium sulfate is an important exception to this rule. For B, rule number 1 indicates that table salt, NaCl, is soluble because it is a salt of an alkali metal. C is an example of two rules contradicting each other. Rule number 4 states that bromides are usually soluble, but rule number 3 states that salts of silver are insoluble. Because rule number 3 precedes rule number 4, the compound is insoluble and will form a precipitate. Second example. Predict if a precipitate will form as a result of this reaction. 2NaOH plus K2CrO4 yields to KOH plus Na2CrO4. Consider the products of the reaction. If either is insoluble, a precipitate will form. The first product, KOH, is an example of two rules contradicting each other. Although rule number 5 says that hydroxides tend to be insoluble, rule number 1 states that salts of alkali metal cations tends to be soluble, and rule number 1 precedes rule number 5. Therefore, this compound will not contribute to any precipitation being formed. The second product, Na2CrO4, also adheres to rule number 1, which states that salt of alkali metals tends to be soluble. Because both products are soluble, no precipitate form as a result of this reaction.
Good day everyone, I'm Paul Vincent Escabena from BSME 1B, and our topic is acid-base reactions. The concept of an acid-base reaction was first proposed in 1754 by Guillaume Franouel, who introduced the word base into chemistry to mean a substance which reacts with an acid to give its solid form as a salt. An acid-base reaction is a type of chemical reaction that occurs between an acid and a base and involves the exchange of one or more hydrogen ions between species that may be neutral. The reaction of an acid with a base is called a neutralization reaction. The product of this reaction are a salt and water. Arrhenius theory is introduced in 1887 by the Swedish scientist Svante Arrhenius, that acids are substances that dissociate in water to yield electrically charged atoms or molecules called ions, one of which is a hydrogen ions, and that bases ionize in water to yield hydroxide ions. According to Arrhenius, the acids are the hydrogen-containing compound which give H positively charged ions or dissociation in water, and bases are hydroxide compounds which give OH negatively charged ions on dissociation in water. The concept of an acid, the Bronsted-Lowry theory, was proposed by Johann Nikolaus Bronsted and Thomas Martin Lowry in 1923. It is based upon the idea of protonation of bases through the protonation of acids, that is, the ability of acids to donate hydrogen ions, otherwise known as protons, to bases, which accept them. The fundamental concept of this theory is that when an acid and a base react with each other, the acid form is conjugate base and the base form is its conjugate acid by exchange of a proton. This theory is generalization of Arrhenius theory. That's all, thank you.
What is polyprotic acids? Polyprotic acids are specific acids that are capable of losing more than a single proton per molecule in acid-base reaction. In other words, acids that has more than one ionizable atom per molecule. Example of polyprotic acid. Sulfuric acid. Sulfuric acid is the strongest polyprotic acid. It has the highest acid ionization constant. And the weakest is phosphoric. Strength of acids and bases. How do you determine the strength of an acid? The bond strength of an acid generally depends on the A of atom. The smaller A of atom, the stronger the H and A bond. When going down a row in the periodic table, the atoms get larger, so the strength of the bonds get weaker, which means the acid gets stronger. How do you determine the strength of a base? First, the less electronegative an atom, the more basic it is. Second, if electron density can be delocalized by resonance, the molecule is a weaker base, as 7 is less interested in losing electrons and accepting a proton. Acid and bases are measured in pH scale. That's all for strength of acids and bases.
Oxidation. Oxidation is defined as a process in which electron is removed from a molecule during a chemical reaction. The term oxidation is used to describe reaction which metal react with oxygen in air to produce metal oxides. As an example, when iron is exposed to air with the presence of water, as an iron will turn to rust, which will produce an iron oxide. For the assigning oxidation state, rules for an assigning oxidation state is first is the oxidation state of an atom in any pure element, whether monatomic, diatomic, or polyatomic, is always zero. The oxidation state of a monatomic ion is the same as this charge. For example, is the sodium is +1 and the chlorine is -1. The oxidation state of fluorine's chemical compounds is always -1 and have oxidation state also for the halogens, except when combined for oxygen and other halogens. Hydrogen is assigned with the oxidation state of +1 in its compound with nonmetals and -1 in its compound with metals. Oxygens have an oxidation state of -2 in compounds with 2 exceptions, when it contains oxygen to fluorine or oxygen to oxygen bonds, with the OS of oxygen is determined by oxidation state of the other elements present. The sum of the oxidation state of all the atoms in neutral molecule of an ion must equal to the charge of the molecule of the ion. The examples is the magnesium chloride. Magnesium chloride, +2 for the magnesium and -1 for the chloride, which is -1 multiplied by +2 equals to -2 multiplied by +2, which is equal to 0, which is neutral oxidation state. Second is the sodium sulfide, which is having an +1 charge and the not being a -2 charge, which is 2 multiplied by 1, which is having a +2, and -1 multiplied by 2 is equals to neutral, which is 0.
Types of redox reaction. Combination. Combination reaction combine elements to form a chemical compound. As usual, oxidation and reduction occur together. Decomposition. Decomposition reaction are the reverse of combination reaction, meaning they are the breakdown of chemical compound into its component elements. Displacement. Displacement reaction, also known as replacement reaction, involve compound and the replacing of element. They occur as single and double replacement reaction. Combustion. Combustion reaction always involve oxygen and an organic fuel. In the following image, we see methane combusting to release energy. Disproportionation. In some redox reaction, substances can be both oxidized and reduced. These are known as disproportionation reaction. One real-life example of such a process is the reaction of hydrogen peroxide, H2O2, when it is poured over a wound. At first, this might look like a simple decomposition reaction, because hydrogen peroxide breaks down to produce oxygen and water. Redox reaction of solid metals in aqueous solution. A widely encountered class of oxidation reduction reaction is the reaction of aqueous solution of acid or metal salt with solid metals.
A single displacement reaction, or sometimes called a single replacement reaction, is a reaction in which one element is substituted for another element in a compound. The starting materials are always pure elements such as pure zinc, metal, or hydrogen gas. Here's the general form for a single replacement reaction. Here's our single element or lone element all by itself, and that single element is going to replace a second element. Here's the second element B, and that second element is in this compound BX. So what happened basically is A. The single element kicks B out, and then we have another single element and a compound on the product side. The easiest way to recognize a single replacement reaction is if you have a single elements or lone elements and the compound of the both sides of your chemical equation. There are two different kinds of single replacement reaction. We have cation replacement and anion replacement. Cations are positively charged ions are metals, so we have a metal replacing a metal. So here's the zinc is our single element. It replaces the second element's copper, and therefore we are going to have copper by itself. The zinc kicks the copper out, and then we have the zinc chloride. For anion single replacement, we have our anions are negatively charged, are non-metals. So the bromine here is going to kick out the iodine, and then we have our iodine by itself, and then we have potassium bromide. So once again, we have a single elements and a compound both sides of the chemical equation.
Today I will discuss how to solve molarity. So before we proceed to the sample problem, let me discuss first what molarity is. So molarity, the most common unit of concentration, and also like the most useful calculation involving the stoichiometry of reactions in a solution. So the molarity defined as the number of moles of solute and presence exactly at 1 liter of solution. So we proceed to the sample problem. This is our sample problem. Calculate the molarity of a solution prepared by dissolving 9.8 moles of solid NaOH, sodium hydroxide, in enough water to make 3.6 liter of solution. Define molarity. You take mole of solute divided by liters of solution. So we have molarity equals moles of solute. The moles of solute here is sodium hydroxide because it getting dissolved in water, and we have 9.8 moles of solute over the liters of solution, which is the 3.6 liter of solution. 3.6. So to find molarity, 9.8 divided by 3.6 liters equals, so I get 2.7. So after that, what should be the units for this? So when you find molarity, the final answer is molar, capital M. So this is 2.7 molar, but what 2.7 molar really means is that there are 2.7 moles of NaOH for every 1 liter of solution. So 2.7 molar, but don't forget that means 2.7 moles for each 1 liter of this solution up here.
Today, I am going to discuss the calculating of moles from the concentration of NaOH. So, let's go to the sample problem. So, yung problem is, calculate the number of moles of sodium hydroxide, NaOH, in 2.50 liters of 0.100 m NaOH. So, yung given natin is identity of solute and volume and molarity of solution, which is ito, 2.50 liter at saka 0.100 mole. So, sa problem na to, ang hinahanap natin ay amount of solute in moles. Kaya yung gagamitin natin yung formula is moles NaOH equals V times molarity mole over liter. So, eto yun. I-input muna natin sa problem. Ang given natin dito sa volume ay 2.50 liter. 2.50 liter. At i-multiply natin sa, para makancel ito, i-multiply natin sa mole over liter. Yung mole natin is 0.100 mole. Over yung liter natin. Per liter to. 0.100 mole per liter. 1 liter. So, i-cancel muna natin yung liter. Tapos, makukuha na natin. I-multiply natin to para makuha yung final answer. Ang final answer is 0.250 mole of NaOH.
The preparation of a solution. To prepare a solution that contains a specified concentration of a substance, it is necessary to dissolve the desired number of moles of solute in enough solvent to give the desired final volume of a solution. Illustrate this procedure for a solution of cobalt-2 chloride dehydrate in ethanol. So take note that the volume of the solvent is not specified. Because the solute occupies space in solution, the volume of the solvent needed is almost always less than the desired volume of the solution. For example, if the desired volume were 1 liter, it would be incorrect to add 1 liter of water to 342 grams of sucrose because that would produce more than 1 liter of solution. So, solution. The molar mass of COCl2 and 2H2O is 165.87 grams of mole. Therefore, mole COCl2 and 2H2O is equal to 10.0 gram over 165.87 gram of mole. It is equal to 0.0603 mole. The volume of the solution in liters is equal to 500 ml. So 1 liter over 1000 ml is equal to 0.500 liter. Molarity is the number of moles of solute per liter of solution. So the molarity of the solution is equal to 0.0603 mole over 0.500 liter is equal to 0.121 m or 0.121 molarity. It is equals to COCl2 and H2O.
Summary of the concentration of solutions. Solution concentrations are typically expressed as molarities and can be prepared by dissolving a known mass of solute in a solvent or diluting a stock solution. Definition of molarity. Molarity equals moles of solute over liters of solution equals millimoles of solute over millimeters of solution. Relationship among volume, molarity, and moles. Volume per liter multiplied by mole per liter is equals to liter times mole over liter equals moles. Relationship between volume, concentration of stock, and dilute solutions. Volume of stock multiplied by mole of stock equals moles of solute
equals volume of dilute multiplied by mole of dilute. The concentration of a substance is the quantity of solute present in a given quantity of solutions. Concentrations are usually expressed in terms of molarity, defined as the number of moles of solute in 1 liter of solution. Solution of a known concentration can be prepared either by dissolving a known mass of solute in a solvent and diluting to a desired final volume, or diluting the appropriate volume of a more concentrated solution, a stacked solution, to the desired final volume.
To proceed, we are now going to discuss titration. In chemistry, titration, also known as titration, is the process that determines the quantity of substance A by mixing it with the exact increments of substance B. The titrant that only reacts when the exact chemical equivalence is achieved. According to Merriam-Webster, it is also defined as the process that determines the concentration of a dissolved substance in terms of the smallest amount of reagent of a known concentration requires to bring about the given effect of a reaction with known volume of the test solution. To further discuss stoichiometry, we provided an example on how to determine the concentration of an unknown solution using titration. The next video will contain an example and their solution.
Consider the following acid-base reaction. We have hydrochloric acid and sodium hydroxide, yielding sodium chloride and water. If 50 milliliters of an HCl solution with unknown concentration are titrated with 0.250 molar sodium hydroxide, if it takes 35.23 ml of base to reach the equivalence point, what was the concentration of the HCl solution? We need to remember about the equivalence point, where the mole of acid equals moles of base. So it's the point where all the acid has been neutralized by the base. Since we want to find out the moles of acid, let's find the moles of base. Let's take our volume of base. We have 35.24 ml sodium hydroxide times 1 over 1000 ml. So we need to convert to liters. So yung nakuha natin ay 0.03524 liters sodium hydroxide. Now, since we have the concentration of the base, we can convert liters into moles. So let's take our liters of base and multiply it by 0.250 moles per liter. And that means that was 0.00881 moles of base that were required to reach the equivalence point. Now we have to look at the stoichiometric ratio of the acid in the base are in the 1-to-1 ratio. So that means if that many moles of base were required to reach the equivalence point, then we multiply by 1 mole of acid over 1 mole of base, and we get the same number of moles back for the acid. When the equivalence point was reached, that many mole of base had precisely neutralized that many moles of acid, and that is the number of moles of acid that were in solution initially for the HCl solution. So now all we need to do is convert that many moles of acid into a concentration. And so concentration is moles per liter, so we take our moles of acid and we divide by 0.0500 liters, and we get 0.176 molar HCl, which was the concentration of our unknown HCl solution.
Our topic for today is all about determining the concentration of an unknown solution using a titration. What is the type of reaction used to determine the concentration of an unknown solution? But before we start, what is titration? A titration is a technique where a solution of a known concentration is used to determine the concentration of an unknown solution. A titration is a process of chemical analysis in which the quantity of some constituent of a sample is determined by adding to the measured sample an exactly known quantity of another substances with which the desired constituent reacts in a definite known proportion. Determining the concentration of an unknown solution using a titration. A chemical nature of a species present in the unknown dictates which type of reaction is most appropriate and also how to determine the equivalence point. The volume of titrant added, its concentration, and the coefficient from the balanced chemical equation for the reaction allow us to calculate the total number of moles of the unknown in the original solution. At the equivalence point of a titration, an exactly equivalent amount of titrant has been added to the sample. The experimental point at which the completion of the reaction is marked by some signal is called the endpoint.